Here we go. All right, so yesterday we left off talking about the two forces that impact your life on a daily basis, gravity and electrostatic force. So there's a whole bunch of different ways that the electrostatic force impacts you. So first of all, if we didn't have the electrostatic force, we wouldn't be here having this discussion. If atoms never combined together to produce something more complex, like if hydrogen and oxygen never combined to produce water, if carbon couldn't hook up to make chains, if you couldn't make DNA, we wouldn't be here having this discussion. We could have had the Big Bang, we could have had hydrogen, but that would have been the end of it. So we would have all of this mass in this universe and nothing to show for it. So conveniently, we can hook molecules together. We figured out how to do that. It's kind of a cool deal. So going into the 1900s, they thought, hey, science is done. We had the Dalton's atomic theory. We kind of understood gravity. We kind of had things going our way. But then along comes J.J. Thomson. So from your Chem 1 days, what did J.J. Thomson do? Oh, dear Lord.
I don't think Miss Hasman told us about JJ.
Okay.
Miss Shirts didn't cover old J.J. Thompson.
Okay.
Probably did.
Okay. I'm guessing that she did, and you slept since then.
No.
Yeah.
Let's call it right now.
Thomson discovered one of the 3 subatomic particles. So you have a choice. It's either electrons.
Electron!
Yes, he found electrons.
Didn't he have the pudding theory thing?
No, well, that led to that.
Oh. Like, wasn't that him?
So, what Thomson did is that he basically hooked up what's called a cathode ray tube, which is basically a glass cylinder, and you had a gas in here, and he hooked it up to a high voltage source, okay? And you passed a current through here. And they'd had this for years, but they really didn't know what it was. They didn't know if these particles was it light, was it positively charged, negatively charged. They didn't know. So Thomson, in the short version of what he did, like we did yesterday, he took a negatively charged object like a balloon. Okay, he used something more high tech, it actually hooked it up like a battery. Like a battery has a positive and negative plate. That's what he did. So he sandwiched this thing between a positive and negatively charged plate. And oddly enough, here was the positively charged plate, and these particles were deflected up towards the positively charged plate and away from the negative plate. So he goes, wow, okay, these particles have a negative charge. Cool. So, and it wasn't, the genius of what he did wasn't just finding the negatively charged particles. He found what's called the charge-to-mass ratio. So, the amount of charge on a proton or electron is a very specific number measured in coulombs. It's 1.6 times 10 to the negative 19. You don't need to know that number. But every proton and every electron that exists in the entire universe has the exact same amount of charge and has the exact same mass. Every electron we have ever studied has always had the exact same mass and had the exact same charge. There's no variance. This is like the ultimate cookie cutter factory. Every electron is the exact same. Every proton is the exact same. Same mass, everything. All protons are identical, all electrons are identical. Except for what we call spin, which is basically which direction they spin, clockwise or counterclockwise. So, these electrons are these very, 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 very small bits of matter. Okay? And the only reason that they really even have matter at all is because they're moving. That's Einstein's theory of relativity. So the cool thing is that they all have the same amount of charge. So this started this whole plum pudding idea. So that everybody goes, okay, well if there's negatively charged particles, what else does there have to be? Positively charged particles, right? Because if you just have negatively charged particles in the universe, guess what? We won't be here having this discussion. Because you would never get things to bond together if all you had was negatively charged. And we're basically neutral, okay? So everybody says, okay, well there can't be negatively charged particles, there has to be positively charged particles. So that led to this whole idea. It's a very British thing because a lot of this work was being done in England at the time. And so they came up with this very British thing called the plum pudding model, okay? And they said, okay, the atom, which came from Dalton's atomic theory, they viewed it as this very, very, very small chunk. And if you stack chunks of this material together, you get squirrels. If you stack them another way, you get Oreos. If you stack them another way, you get Lexi. Okay? So depending upon how you stack these things, you get different compounds. And so they said, okay, the positive and negatively charged particles were kind of evenly distributed. So they conceded the fact, they said, okay, we have negative charges, there has to be positively charged particles. It's neutral, so this is a nice way to balance this out. Because they knew that the protons would repel each other, but then that would balance out because the protons would be attracted to the electrons, and it was a nice little harmonic situation and life was cool. So this was good for a while. Then along comes Ernest Rutherford. Anybody remember what Ernest Rutherford did? He did what?
He discovered something.
He discovered something.
Proton.
Close.
Neutrons.
The electron.
Electron cloud. He organized the periodic table.
That was Mendeleev.
Yeah.
Come on, dude.
He came up with Galileo's law. I'll forgot his number.
Just shut up.
He came up with Galileo's
How about
law.
the gold
And
foil?
Avogadro's number.
Gold foil. Does anybody remember the gold foil experiment?
Oh,
Oh, that was when they took the.
Really?
boy.
Okay. Rutherford's gold foil experiment is the most misunderstood thing that happens in the entire world. So you have to understand a couple of things about the situation. This is in the early 1900s. Okay? They were searching for the structure of matter in the universe. Now, here's an annoying thing that the chemistry teachers don't like to talk about. Everybody that was doing this research weren't chemists. They were all physicists. Okay? So Thomson was a physicist. Rutherford was a physicist. Rutherford's famous quote was, "The only real science that exists is physics. Everything else is stamp collecting." Okay? So these are physicists. Now, you have to understand how physicists view the world. So here's the classic example. Okay? Rutherford was a physicist, and he was this large guy. He was actually from New Zealand, had a really cool handlebar mustache. He was a very loud, boisterous guy. So here's the classic idea of how physicists approach a problem. You give a Volkswagen Bug to a physicist, and you go, "Hey, what's made up of, what is the Volkswagen Bug made of?" He goes, "I don't know, but I got a wall, and I can smash the car into the wall." So the physicist gets the car up to like 30 miles an hour, and he smashes it into the wall. "Oh, great, there was a bumper." "All right, well, a bumper was part of the car." "Okay, cool." And then he goes, "Well, 30 is good. 300 miles per hour is going to be better." So then he gets the car up to 300 miles an hour, and he smashes that into the wall. He goes, "Wow, look, now there's parts inside of the car, like there's a seat, okay, and a rear view mirror, and there's paint that's come flying off. Okay, we're getting somewhere. Well, if 300 is good, 3,000 is going to be even better." So then we get the car up to 3,000 miles an hour, smash it. "Wow, there's an engine inside the car. Cool. Okay, well, what's the engine made of?" "I don't know. Let's get the engine up to, I don't know, say 300,000 miles an hour. And we'll smash that into the wall. Oh, look, there's pistons. Oh, cool. What are the pistons made of?" "I don't know. Let's take 2 pistons and get those up to like the speed of light and smash the pistons together. And we'll see what goes flying off." And that's literally how they found the structure of matter. Okay? They were physicists. They weren't chemists. They weren't doing little, "Oh, here's a test tube, and let's mix stuff together." No, they were physicists. They wanted to smash stuff together and see what came flying off. Which is why, if you do any research, there's something called the Large Hadron Collider, which exists on the border between Switzerland and France, and that's basically what they do. All particle colliders, basically, we smash stuff together at high speeds and see what goes flying off. That's how physicists approach the problem. None of this Nancy, "Ooh, look, let's make math." No, let's smash stuff together. Okay, so, no, it's true. Okay, so let's talk about what happened in the gold foil experiment. Because here's the diagram that is in every book, and it's wrong. They go, here's like this little box, and then they show like rays coming out and hits the gold foil, and they've got this little kind of thing drawn around here and all jacked up. Okay, so here's basically what happened, the short version. This is a whole hour and a half long lecture that I'm going to condense into like 5 minutes. So he had a radioactive source inside this box, radon-234. And what it would do is it would emit radioactive particles. He didn't know what they were. Okay? They knew that these particles were being emitted, didn't know what they were. So he called them alpha particles. First letter in the Greek alphabet, because he didn't know what they were. Now, you can't see them. Okay? These alpha particles are individual. It turns out that they were helium nuclei. So, if you remember your chemistry in 4,2He2+, this is the mass number, total number of protons and neutrons. This is the number of protons, which is 2. We've stripped off 2 electrons. So basically, what Rutherford was calling an alpha particle was a helium nucleus without the electrons. So it was positively charged. He didn't know what it was. That's why I called it an alpha particle. So these particles were being emitted. You couldn't see them. So how they detected them was they had this phosphorescent screen, which is basically how the old televisions used to be made. And these particles, when they would hit this phosphorescent screen, would emit a small, like, burst of light. Okay? So that's how you can see where the particles hit the screen, is that you would see this burst of light. You can't see the particles. So I want to scream every time that, a chemistry book draws this like it was like this ray coming out. Okay? No, it's bad. You couldn't see the particles. So what he did is he had to figure out if they were positively charged. So he basically stole a page from Thomson. So he knew these particles were coming out, and he put a positively charged plate and a negatively charged plate on either side of this stream of particles. And what he found was that these particles were deflected away from the positive and toward the negative. So these were going in the opposite way that the particles that Thomson did were traveling. Yes, Garfield?
So why was he doing this experiment in the first place?
This is because he was searching to understand the fundamental nature of the universe, what stuff is made of.
All right.
Okay? All right. So he figured out that they were positively charged. Okay, cool. Now, he knew that they were bigger than electrons, and here's the reason why. Here's the good analogy. Let's say that I take Hank, okay, and I've got a blow dryer. And I roll Hank by the stream of the blow dryer. Okay, Hank's going to move a little bit, but not very much, because he's got a lot of mass. If I take a golf ball and roll that across in front of the blow dryer, the golf ball is going to move a lot further, because of the fact that it has less mass. So that's basically how I figured out. These particles weren't deflected as far as the electrons were, so he knew that they were positively charged, and they were more massive than the particles that Thomson had found. Okay, so then he takes gold foil. And the cool thing about gold foil is that literally you can pound this stuff into basically where it's a single layer thick. Okay? And it's almost like, it's actually thinner than paper. Gold foil is thinner than a sheet of paper. So he stretched this gold foil. He had the particles here being emitted. This is in a darkened room. If you were a graduate assistant working with Rutherford, it sucked, because you were sitting in a darkened room with a radioactive source emitting particles that we called alpha particles. You didn't know what they were. There was a gold foil. You were surrounded by this phosphorescent material, and you had a piece of paper, and you were making tick marks on the piece of paper wherever you saw the flash of light. It isn't like they had computers where you could model all of this stuff. This was 100 years ago. Literally, you were sitting in a room making tick marks wherever you saw the flash of light. That was it. Pretty boring. And they did this for a long time. They had like millions upon millions of tick marks on this deal. So what they found was that most of the flashes of light occurred directly behind that gold foil. So here's the analogy. It would be like me taking Hank, and I'm going to put Hank in the very back of the room. I'm going to stand down at 21st and Mays Road, 4 miles away, and I'm going to start shooting golf balls at Hank. Okay? I'm 4 miles away. On a relative scale, this is about how it works out. And I'm going to shoot golf balls at Hank. Most of the time, what are the golf balls going to do?
Hit something.
they're going to miss. Okay, I'm trying to hit this bowling ball from 4 miles away. Most of the time, it's going to miss, right? Most of the time, it's not going to be deflected. Every once in a while, it might hit and bounce off and be deflected a little bit. Not very often, right? Now, every once in a very, 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 very great while, it's going to hit exactly square and it's going to bounce back to me at 21st and Mays Road. Okay? But that's going to be a pretty rare occurrence because I'm trying to hit a target that's a long way away. That's what they found with the alpha particles. The alpha particles, for the most part, went straight through. Every once in a while, they would hit and you would see a flash of light back here. But it happened like 1 in a million. So it would be like me taking this golf ball and I'm going to throw it at the wall, okay? And I'm going to do this a million times. And most of the time, the golf ball goes straight through the wall. But 1 in a million, that golf ball is going to hit and it's going to bounce back. What am I going to conclude about that wall? Even though it looks solid, it has to be what?
Porous.
Yeah, mostly empty space. So that's what he figured out about this gold foil. So he goes, hey, these gold atoms, the plum pudding model where everything's evenly distributed, no, it's wrong. All of the positive charge has to be located in an extremely small, dense area. Now, he knew that they were positively charged because the positive charge would approach, store potential energy, and go flying back. So the only way that you can make a positively charged particle bounce back is if it hit another positively charged nucleus. So here's the 2 things that you have to came out of Rutherford's theory. The nucleus was very, 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 very small, but very, very massive and positively charged. Now, this created a problem. So here's the classic analogy. If you consider like a football stadium to be the size of an atom, the nucleus is like maybe a grapefruit on the 50-yard line. Okay? All of this is empty space created by the electron cloud. But this contains 99% of the mass. So everything, this table, you, everything is about 99.9% empty space. So you're going, no it's not. Look, it's solid. Okay? That's because of the electron cloud creating basically a repulsive force. You are 99.9% empty space. Everybody is. All the structure in the universe is about 99.9% empty space. And don't flip out and go, wow, that's weird. Yes, it is. And here's another thing. You've never actually touched anything in your entire life because the electrons in your hand are repulsed by that. And you go, well, I feel it. You feel the repulsion of electron clouds. That's what you feel. You've never touched anything in your life. And don't flip out and go,
I'm touching.
Wait, so you can't touch electrons then?
no. Well, no, they
So
just
why do you
repel
think
each
it's
other.
still different then?
Huh?
Shouldn't if it's just like repulsion?
It's just interactions with the electron cloud.
So if you like get smashed into a wall like a million miles an hour, you're not going to touch anything?
Not on an atomic level. Now, it's going to be a bunch of interactions, yeah. But because all you're interacting is empty space. No, that's when it's positively charged particles.
What if they positively charge you? Like,
Yeah.
No, we got to get through stuff. Don't, we can overanalyze this stuff, and we're not.
I'm talking about
Okay.
this dude's experiment though.
What about it?
Okay, you say that there's that small chance that you hit.
Yes, that positively charged is going to come in and hit that positive charge.
So there's no way that you could ever hit that, like when you touch an object? You can't hit
No, because this was a positive charge going through and hitting a single layer of atoms.
We have electrons.
Yes. Yes. Okay. Now, so this created a problem for the scientific community, and it was a huge problem. This was huge. Now, I can make this analogy because I grew up with 3 older sisters. Okay? The problem with this is that you have all of these protons that don't like each other, hate each other, loathe each other, don't want to be anywhere near each other. But yet they're all confined into an extremely small space. So it'd be like 8 girls that hate each other. Back in 7th grade, somebody said something on Facebook, and or posted a picture on Instagram and they're still holding a grudge, okay? Like these girls, like if one sees the other one walking down the hall, they're gonna go down the other hallway just so they don't run into them in the hall. They don't like each other. But you take those same 8 girls and you can find them inside a Volkswagen Bug. They are the best of friends. Okay, there's the strongest bond that exists. BFFs. Oh, let's take selfies. Oh, okay, right. Oh, post something on my Facebook. Oh, I love you. Okay, right. But yeah, you laugh, but it's all true. But that only happens if they are confined within a Volkswagen Bug. If you get them outside of that Volkswagen Bug, they automatically hate each other again. So what happens with protons is that they had to come up with a new force. And this was not very clever on the physicist's part. So they said, okay, there has to be a force that's stronger than the force that wants them to repel because they have the same charge. Okay? Because that's what they want to do. So the new force has to be stronger than the electrostatic force. They called it, wait for it, the strong nuclear force. Yes, not very clever, but it works. So the strong force, oddly enough, and I'm going to ask you this question. I'm going to tell you, this is going to be one of the multiple choice questions you're going to have on the next test. And I'm going to ask you, what is the strongest of the 4 fundamental forces? Don't miss the question. It's the strong force. Okay? I'm going to ask you that question.
Strong force is the strongest force.
Yes. Okay? Don't miss the question. I'm going to tell you straight up. I'm going to ask you that question. But every force has to have a charge carrier to make it happen. The electrostatic force is carried by photons. So yesterday when I was picking up the little bits of paper with the balloon, that was actually being done by photons. With gravity, we think they're supposedly particles we've never been able to detect them, called gravitons. So when I let go of the marble, gravitons are making it accelerate. We've never been able to find them, but it's a catchy name. So the strong force, which basically holds together the nucleus, the strong force is supposedly carried by particles called, and this is better, called gluons, because it glues the nucleus together. So the strong force is carried by gluons, the electrostatic force is carried by photons, the gravitational force is carried by gravitons. Okay? And interactions with people are carried by persons, and then you have solids where you have croutons. So it's all just one big mix. Okay. All right. So the only thing, now, the strong force is pretty important. It doesn't impact your daily life, but if all of a sudden the strong force stops working, very bad things are going to happen. Every nucleus of every atom inside of your body is immediately going to go flying apart. Okay? It's bad, because the protons don't want to be together. But the good thing about nuclei is that they're very stable. I don't have to worry about walking in here tomorrow or Monday morning and my table is turned into like a cat, okay? This table is older than you guys are. It's every day I walk in, I worry about a lot of things. I don't worry about that thing being something different. It's stable. You don't have to wake up tomorrow morning and go, okay, good, I'm all together. Okay, no, none of my protons have changed. I'm good, okay? So you don't worry about that. It's cool.
How do you say that again?
Inclinatio ad quitum. We good? It used to be you had to study Latin, mainly because if you ever do go into like the medical field, take a class in Latin, because so many terms in the medical field especially have a Latin base. So it's actually to your benefit to learn Latin.
We were talking more like, it sounds like a Harry Potter spell. Like
You're done.
Yeah, either that or like a fancy like Mexican meal. Give me the inclinatio ad quitum. Okay. All right. Now there's one force left, and that's the weak force, which is important. I'm not going to ask you anything about it, but the weak force. If you don't have the weak force, you don't have like the sun, because you don't have fusion process where the hydrogen is combining in to make helium. So the weak force is important. We wouldn't exist in the universe without it, but it's not something that we're going to worry about. Okay, so that's the big picture.
So the strong force, gluons, right? That's the,
Yes.
you've never been able to detect those.
No, they're proposed that they exist. We've never been able to detect.
It's just a theory.
It's all an idea, right?
Kind of is.
What is he driving?
But we know it's there, we know it has to be charged, period. Okay. So, one of the different ways that the electrostatic force plays out is creating friction. Okay? Now, there's two types of friction. We call static and kinetic. Static is from rest, and kinetic is from the Greek word meaning motion. So if you're going into like physical therapy, you're going to take a class called kinesiology, which is the study of motion. Yes?
I have a question.
Yes.
On the notes, is this supposed to be electrostatic or electromagnetic?
It's the same thing.
Okay.
Wait, what?
It depends on which book you look in.
Okay.
Yeah, but it's the same thing.
Did we get a book in this class?
No, I'm just saying depending on the textbook.
So on this note sheet,
What?
You don't need to stop. Don't even use this.
Is this on there?
What? Yeah, it's on the
Static
back
and
side.
kinetic friction.
Should be on the back side.
That's where 3 laws of motion.
It's in the middle
It's in the middle, yeah.
of the equation.
Manifestation of forces. Okay, so here's the deal. And this is what you have to understand in terms of the big picture. So, and this goes back to this whole idea of inclination, equilibrium. So, if this was the magic frictionless block, and I gave it a push, what would it do?
It would go forever.
It would go forever in a straight line at a constant speed.
Did we ever get that thing charged?
No, I couldn't. I could never find the right charger, which is just weird because I had 2 of them. So, okay. Now, so the only reason it comes to rest is because of friction. Now, this is going to be important. So, when you look at this block or you, there's always forces acting on it. We're sitting on this rock. So, the one force that is always present is gravity. So, when you look at this block, and we'll get the friction here in just a second. We have to have a quick deviation from gravity. Gravity always acts, it technically doesn't act, everybody says, oh, gravity acts down. No, it really doesn't, and don't flip out when you look at this. Technically, gravity always pulls in towards the center of the earth. So, if I'm here in Kansas and I drop something, it actually almost falls sideways, okay? And it gets really weird, like if you're on the South Pole and you drop something, it actually falls up, okay? Like towards the center of the earth. The only way it actually...
Well, it depends how you look at it.
I know, but I'm just saying, so technically down isn't right. It just always falls towards the center of the earth.
So if like your reference point is from like the moon, it would
Yeah.
look like
Yes.
it's falling. But if your reference point is here, then it looks like it's falling down towards
Yes,
the
but I'm
ground.
just saying, it's just always falling towards the center of the earth.
So the
In
ground.
the big
Okay.
picture.
If you, so.
No, don't.
You don't
don't.
pull the earth at all? Like me as a person, I don't pull.
Yes, you do. It's Newton's third law. We'll get into that. Okay,
Maybe second law.
so this and we're going to deal with a whole bunch of different forces. Okay, gravity is one of the biggest ones that we're going to deal with because it's the most pervasive. So there's 2 ways that you can determine the gravitational pull. One is that you multiply mass times your gravitational acceleration. You did this the very first day that you were in this class with the spring lamp. Okay? So if I've got like a 2 kilogram mass, I'm going to take 2 kilograms times 9.8 meters per second squared. Now, here's amongst my list of pet peeves that will drive me nuts. Don't tell me this. How do you calculate the gravitational pull? Don't go, oh, that's mass times gravity. I will flip out. This is not gravity. You cannot multiply mass by gravity. You can multiply it by the gravitational acceleration caused by gravity. Okay? But you cannot multiply it by gravity. Don't say, this is mass times gravity. I will flip out. Okay?
So it's mass times the gravitational acceleration.
That I can live with.
That's
What
a
would you
word.
look
just
at?
say
Which do you hate
acceleration.
more, deceleration or when people say that?
It's a tie.
Really?
It really is.
Really?
Like time.
Decelerating due to gravity.
I mean, either one of them, you say, oh, I'm decelerating because of mg. That ties it all together. Okay. Now, so here's always the big debate. Do I make it negative or do I make it positive? If I just say, hey, here's a 1 kilogram mass, and I want to know what it weighs, okay, and weighs is the same thing as gravitational pull. So when you step on a bathroom scale in the morning, it works because the earth is pulling you down and you're exerting a force on that bathroom scale. So if you have got 1 kilogram mass, I multiply that by 9.8 meters per second squared, I get 9.80 newtons. So the question is always, do I make it positive or negative? If all I'm asking you is, what's the gravitational pull? Just give me the number. Now, if I talk about it in the context of the lab, like you're going to do, and we have to make all of the forces add up to equal to 0, then it's defined as being a negative value. So you can't go wrong if you make it negative, but you don't have to. The only time it really has to be negative is when you're drawing vectors or when you're adding together forces. So if you don't want to have to think, hey, I'm just always going to make it negative, you don't have to worry about it then. Okay, so let's just say, all right, we don't have to think about it. Cool. Boom, negative. That's one way to calculate it, is if you know the mass, multiply it by your gravitational acceleration, boom, there's the force. That's one option. The other option, and this is what we're going to use, are Newton scales, because oddly enough they measure in newtons, and they're scale. So we're going to be using these a lot. And these, there's different ones, like this is a 2.5 Newton scale. This is a 5 Newton scale. I've also got 10 Newton scales. So the rule with these scales is you always start with the smallest scale first and work your way up. So if a 2.5 Newton scale will do it, use a 2.5 Newton scale. If you hook it up and it basically bottoms out the 2.5 Newton scale, go to the 5 Newton scale. Okay? If that won't work, go to the 10 Newton scale. Mainly because you always want to use the most precise measuring device that you can to start with. So the other thing that happens is sometimes you'll be lifting stuff, sometimes you're going to be pulling stuff. So what you want to do is make sure that these scales are re-zeroed because they work on a spring that's inside of here. So basically, I've got it like this. I'm going to lift this block. So I'm going to set this up right. I'm going to grab that tab. I'm going to re-zero it. Boom. I'm at 0 newtons. So then I'm going to take this block, hang it up, and I read it this way. So the other thing that I can do is just, if I want to find the weight of something, or the gravitational pull, just hook it up to a Newton scale. See what it reads, boom, there's my number. I don't have to multiply by anything, because this is already in newtons, okay? So I do this, I get 2.18 newtons. So what this means is that when I set this block down, every proton, electron, and neutron that makes up this block is attracted to every proton, electron, and neutron on this rock that we're sitting on. And the sum total of that interaction and every particle on this rock that we're on, when you add them all up, only adds up to 2.18 newtons. Now if you think about it, that's not very much. I mean, the Earth is pretty big, okay? It's really, really big, okay? But this is attracted to the Earth. But all of those forces added together only get you 2.18 newtons. So there's the, oh, gravity is such a strong force. It is, but it really isn't all that strong compared to the other forces. So right now, I've got this force acting down. I'm going to make that negative 2.18 newtons. Now, why isn't it accelerating and falling towards the Earth? Kyle?
Well,
it's a deep subject.
yeah, it is.
Okay?
You said it's just attracted to the Earth, but it's not, so I'm confused.
It is attracted to the Earth.
But not just the Earth.
Oh no, it's attracted to the Moon and Saturn and you and Hunter and the
So
camera.
it can get so much more complicated.
It was always
Well, it can, but that's where we treat stuff as what we call point mass. We'll get into that when we do gravitational fields. Don't overthink it. Kyle, why isn't that block falling towards the center of the Earth and do burning ember of oblivion.
Wow.
I know it's a little extreme.
Yeah.
Because gravity's not that strong.
Oh yeah, it is. Gravity's pulling it.
I don't know.
Because of, what's this? Let's articulate the thumb tap.
The table.
The table is providing a force that's balancing it out, right? Okay? So the table is providing what we call a normal force. Now, this N means normal. Okay? Normal. Now, there is not eventually like going to be an abnormal force. Okay, it isn't like, wow, if it's really weird, we call it the abnormal. No, it's a normal force. Now, technically, for now, this won't matter for now, but it will later on. Technically, force normal is equal to Fg cosine theta, and this is what I have on your equation sheet. So, the cosine theta is the angle of the incline. Well, if you're at 0 degrees, what's the cosine of 0?
0. 1.
1. Cosine of 0 is 1. So on a flat surface, guess what? Force normal is just the same as Fg. Okay? Later on, when we get into inclined planes, we will have to worry about this angle. But for now, we don't have to because everything's going to be on a flat surface. Yes? You
No.
seem...
No.
No? What?
Fn can't equal Fg. Otherwise, they both go through the floor.
But the force normal is going to be acting upward.
So in that case, you would want the negative sign.
Yes. So I want this to be negative, and then my normal force would be a 2.18 Newton. This just gets you the magnitude of it. Okay? Now, it's a simple idea, but it's important. If I take 2.18, which is the force, upward force provided by the table, and add that to a negative 2.18, what do I get? 0. So that means the net force acting on the system is 0. Now, every problem, listen to me, every force problem that you are going to work will only be one of two categories, and only one of two categories. You're either at a constant velocity, which could be at rest, it could be at 10 meters per second, it could be at negative 300 meters per second, doesn't make any difference. If you're at a constant velocity, all the forces add up to equal to 0. That's it. Boom. So if you ever see constant velocity, you make all of the forces add up to 0. The other option, if you're not at constant velocity, what are you doing? You're accelerating, right? And then guess what the forces don't add up to? 0. Literally, every problem that you are going to do with forces is only one of two situations. You're either at constant velocity and you make all the forces add up to 0, or you're accelerating and they don't add up to 0. That's it. There is nothing in between. Yes?
Is that a force equation up there? Or what kind of equation?
What do you mean?
At the top.
This?
Yeah.
Force normal equals Fg cosine theta?
Yeah.
Yeah.
I know
It's on
this.
there.
I'm making sure. What is it for? What kind of equation? What is it for? What is it
It's for calculating a normal force.
Alright. Shut up. You've been sleeping. Go back to sleep.
I literally just read it off the paper.
Yeah, it's on your equation sheet.
Well, I'm having a hard time. Maybe if you bold stuff for me.
Bold
I
stuff.
would like it. I'm used to your bolding. I'm used to your bolding. I can't.
Whoa! How can you bold and
Oh,
I'm used to bold, you boy.
bold anything you get wrong on the next assignment.
Oh.
Okay. Alright. Now,
Nice 43.
if I take this and throw it,
Put that bold mark on his face.
yeah.
It's a bold move.
Okay. Now, right now, is it accelerating?
No.
No.
All the forces add up to?
0.
So instead of the table providing that upward force of 2.18 newtons, my hand is providing that force. Okay? Now, as soon as I let go of it, what does it begin to do?
Accelerate.
Because what did I lose?
Your 0 force.
I lost the normal force, right? So therefore, what's the only force left acting on it? Gravity. Therefore, it begins to accelerate. Okay. Now, if I want to take this and I want to pull it, I want to figure out how much force it takes to pull this thing. So I'm going to lay this flat, I'm going to re-zero it, and I'm going to pull it at a constant velocity. Now listen to what I just said. I'm going to pull it at a constant velocity. So what do I want all the forces to add up to?
0.
0. So I want to pull it at a constant velocity. I'm at about 0.65. Okay?
Alright.
So I'm going to draw this as what we call a free body diagram. So I've got gravity pulling down at negative 2.18 newtons. I've got my normal force at positive 2.18 newtons. Right? Now, I've got a force going in the direction of motion. We're going to call that FAC, which is going to be my force applied, which is going to be 0.65 newtons. Okay?
Man, this negative 2.18 is coming up a lot.
It was just the block that we've got. So
It is. I'm just saying it's coming up a lot.
it is. Now,
Call him Reese. It's a weird call him James. Don't
No
call
one,
him
I've never heard.
Keep calling him James.
Yeah.
Yeah.
He goes by Reese.
Keep
I like James Johnson's fists.
okay.
Actually, James sounds way cooler.
Don't mean anything, just don't call me late for breakfast. Come on.
Alright, so
Now, focus! Focus!
Yeah.
If these were all the forces that were acting on the block, what would it have to be doing, Cubby? Could this thing move at a constant velocity with this set of forces right now?
No.
You're right. Why are you right?
F of Y. F of
I guess.
That's valid.
Good enough.
Because it doesn't equal 0.
What does
I
it
said
equal?
FG.
all the forces.
normal.
Force applied.
Force applied.
Is that an F of Y or an F of G down below?
This is Fg.
Okay.
This is my gravitational pull. Okay?
FN.
So if I take positive 2.18, negative 2.18, and positive 0.65, I don't get 0. Which means this thing should be accelerating in that direction.
But you're forgetting one
But it's
thing.
not. So here's the whole key. What's the only reason I have to apply a force to keep it moving?
Friction.
Yes, there's friction. If there was no friction, I could go dink, let go of it, and it would just move off. So, I hate homecoming. So, if my applied force is 0.65, what do you think my frictional force is?
0.65.
Negative.
Negative 0.65.
In the opposite direction, making it negative.
Hold on. I don't believe that. No. You said if it all equals 0.
It's at a
I'm at a
constant
constant
velocity, and it was.
If it's at a constant velocity.
It's like caveman's covering fire. I just made it.
Okay, good.
I could be wrong.
I know, I can be.
Honestly, imagine how excited I was.
So, yes?
So is there any way,
Hey!
if I was just like looking at this, I would think it's at rest. So would you like, I know it's at a constant velocity, so like how would you know like it's not at rest, if that makes sense? I'm not making any sense. Just keep
How would I know that it's not at rest?
Yeah, that's true. I think that's at rest too.
Okay, it could be, and I'll show you why.
That's what I'm
Okay?
saying it could be, so I'm confused.
I am this far away from making you move to that side of the room. If I have to stop one more time, you're going over there. Is that clear? No, I don't teach freshmen. Yes. Okay. Now, let's say, I'm going to take this and I'm going to apply a force of like 0.3 newtons. So I'm applying a force in this direction. Is it accelerating?
No.
No. Why?
It's not moving.
Why isn't it moving?
You're not applying enough force because the friction is too high.
Because the friction is holding it in place, right? Now, if I apply enough force, it just begins to move. Now, at that point where it just begins to move, this is what we're going to talk about with static friction. My applied force is just enough to overcome the frictional force that's holding it in place. Okay? So, and you would have to be told, hey, this thing is moving at a constant velocity.
Yeah, okay.
Okay?
Yeah, that's
You would
what I was
have,
asking.
yeah. So, looking at that, your constant velocity could be 0.
Yeah, that's what I was
Yes,
asking.
but your constant velocity might be 100 meters per second though too.
Yeah.
Okay?
Yeah.
So like for the cruise control in your car, the cruise control in your car works because it makes all of the forces add up to 0. You're not accelerating. So if you're driving down Maze Road and you set your cruise control at 45, all the forward forces
No, it's
are balancing out the opposing forces created by friction, wind resistance, internal friction within your engine. Okay? So if you had the magic frictionless car, all you have to do is get it up to speed. You could take your foot off the gas and you could just coast at a continuous velocity in a straight line.
And then you could never stop ever.
You know what McClure said?
No.
He said that he's gonna make frictionless roads and make $1 billion.
Okay, problem with frictionless roads is you can't stop and you can't turn.
Just make them
They
straight.
make a frictionless
just
road.
make them straight.
You can't.
It'd be like an
Okay.
air hockey team.
Now, here's the next big equation that is on your equation sheet.
You hear that?
Where at?
Same area. It's this. U equals force friction
You circled that.
over force normal. Okay? So this is the Greek letter mu. It's basically,
I just hit my elbow. I'm so sorry.
okay.
That's it. Move her to the other side of the room. Move her to the other side of the room. I'm tired of these distractions. God, this is why I can't focus.
Okay. So the Greek letter mu is basically like a U with kind of a French thing off to the side. Okay?
Straight down.
And this is also known as the coefficient
My fingers.
of friction.
Did you say correlation?
So,
Coefficient.
coefficient of friction.
She said coalition.
What are you guys talking about? Kyle, why are you trying to come up with your mistakes?
Is this not on?
Okay.
Okay.
So, here's the deal.
I know.
If in this situation, I can calculate the coefficient of friction. So what I'm going to do, I've got my force friction, which is negative 0.65. I've got my gravitational pull, which is the same as my force normal, which is 2.18. So what I'm going to do is I'm going to take that 0.65 newtons. Now, I'm not worried about the negative sign because this is like an absolute value. So there's two things about mu. First off, it's never negative. It's an absolute value. Your frictional force might be negative. I don't care. All I want is a ratio. So we're going to take 0.65, and then I'm going to divide that by that 2.18 newtons. So somebody take 0.65 and divide it by 2.18.
Wish I could.
0.98,
No way it's
0.298, 165,
There is no way this is 0.98.
I said 0.298, 165, 1376.
So call it 0.30. Now, what units
Actually,
do
you
you
can.
have?
Yeah, you can do that, I guess.
What units is mu in?
New.
It's a trick question.
There's
It
no
doesn't
R
have
in
any.
it.
It has no units because it's newtons divided by newtons. Okay? So this is just a number. Because it's just a number and it has no units, it's a scalar quantity. It has no units. So don't ever make this negative. Don't ever put units on it. Okay? It's just a ratio of forces.
Is that the
Okay.
second thing about it?
Huh?
That it's never negative.
It's never negative. The other thing is that notice this is less than 1. 99.9% of the time, mu is going to be less than or equal to 1. Rarely can it get above that if you have really, really sticky surfaces. But generally, under normal circumstances, mu is going to be less than 1. So if you ever calculate mu and you get 5, something is wrong.
Unless you're like
No,
working in tar.
maybe. And you're not. Okay, so I'm telling you, in this class, if you ever get a coefficient of friction above 1, like 2, 3, something like that, something is wrong. Avery,
What's that 2.18?
the 2.18 newtons was the normal force acting on the block. Yeah, that's just the weight of the block. I hung it up, it's 2.18 newtons. Okay. Cool with this?
Yep.
So what does that
I
number
do
mean?
physics, but I don't know.
Okay, basically here's the deal. As mu becomes bigger, that is a reflection of more friction, because I'm not going to change the weight of the block. So if my frictional force to pull it was bigger, this would get bigger. Okay?
So like more friction equals bigger number.
Yes. So like on ice, this is a really small number because it wouldn't take very much force to keep it moving. Now, if it's a perfectly frictionless surface, how much force friction is there? Zero. What's mu going to be? Zero. Okay? So the smaller mu is, the less friction there is. Okay? Cool with that. All right. Now, as I so to speak. Now, here's the deal. This is what we call kinetic friction. Okay? This was moving it at a constant speed. This is kinetic friction. Now, if I want static friction, the measuring technique is a little bit different. So what you're going to do with static friction, and this is what you're going to do in the lab. So you're going to have it at rest, and what you're going to do is you're going to slowly increase the amount of force needed until the point, until it just begins to move. Okay? So I'm going to take this, I'm going to pull ever so gently.
Want me to do it?
No. Until it just begins to move.
Oh.
About 0.95. Okay? So my static friction is the exact same calculation. It's the exact same force normal. Now, Garfield,
Yep.
I want 0.95 newtons divided by 2.18.
Why was it 0.65 the first time?
Because that's how much force it took for me to pull it.
0.4357798.165.
How did that number
So,
change?
just 2 digits.
Why would the...
0.4.
That's what it takes for it to accelerate.
0.44.
That's what it
it's-
takes for constant velocity. That's what it takes for acceleration.
Well, at least to move it from rest.
Wait a second. Wait a second.
What?
So if that's what it took to move it from rest, how did it move at 0.030?
Because this was already, because there's 2 things that are happening. Once at rest, remember it wants to stay at rest.
Alright.
So once I get it moving, it wants to keep moving. Okay? So I've got a couple of things working against me with the static friction.
Oh, okay. So on the first one, like you pulled it a little bit and then you kind of brought it down to 30.30.
No, this was just a measure. All I did was that I pulled it at a constant velocity and I figured out how much force it took to keep it moving at a constant velocity.
Alright.
That's that 0.65 newtons, which generated that 0.3. This was the force it took to pull it from rest. Now, here's what you should generally see. Not always, but generally your coefficient of static friction is bigger than your coefficient of kinetic friction.
When would that not be the case?
Usually it's because of the different types of surfaces if you're comparing them, but generally your static friction is going to be greater than your, just in the lab, if you don't get this, it's just because there might be variances in like the surface itself, okay? But generally your static friction is going to be larger. Not always, but generally it is. Okay, so here's what you have to understand about frictional force. You never directly measure frictional force. What you do is you measure how much force it takes to keep it moving. Once you measure that, then you know what your frictional force is. Okay? So I will never ask you to directly measure your frictional force. You can't. But what you do is you measure how much force it takes to keep it moving. Now, you all have experienced this. If you've ever ridden a bike into a strong south wind. You're riding your bike into a strong wind. What happens to your force applied?
You gotta pedal harder.
Increase
You
it.
got to pedal harder. Why?
Because the wind is.
Yeah, the wind is
More
pushing
friction.
against you. So you have to work, you have to apply more force to overcome the frictional force that's working against you. If you're, imagine someone, you take your car and you walk out and someone's put a big sheet of plywood vertically on top of your car. What's going to happen to your fuel mileage?
It's gonna be terrible.
It's going to horrible because now you have all of this frictional force that you have to overcome. If you look at fuel efficient cars, how are they designed? They're very sleek to reduce the amount of frictional force that they have with the air as they're driving through it. Less frictional force, less drag, your engine doesn't have to work as hard to make it go down the road.
I thought
Okay.
$1 million invention.
Oh, let's hear that.
Oh, let's hear it.
Instead of having side mirrors, I come up with a way that they aren't there, but you can still see. So there's less friction, giving more gas efficiency.
Gosh.
Okay.
Like a rear view mirror.
Yeah.
Inside
it's like-
Okay, so
Yeah,
stop
maybe
that,
see
let's go
behind
back,
It's a side
and let me hand out the lab and we'll talk about that. Okay, so there's two main parts to this lab. The first is going to deal with friction. So you're going to take a block of wood, take scale, read it, boom, there's your FG. That's going to stay the same on all of these columns, because what we're going to investigate is the interaction between this block of wood and different surfaces. So, hang it up, got it, easy peasy. So you're going to do wood on wood, so you're going to lay this thing flat, re-zero it. You're going to measure two forces. The force that it takes to pull it at a constant velocity, which in this case is about like 0.35, and then I'm going to measure how much force it takes to pull it from rest, which is about...
My
Shirt!
teacher,
It's a
not
shirt!
Mr. Birdcamp, Mr.
Yes.
Problems with your trailer, the part.
Here, I'll demonstrate this.
Shut up!
The stand
Yeah.
is, because as we're raising it up, it's, the bottom part's not coming up, so it's lifting my mom's truck up. So.
You're gonna probably need to go help her.
Yeah, I think you should probably
What, I mean, so,
take an
Yeah.
action.
She's got it on there.
Here,
Yeah.
I'll
But
just
on the
clearly
bottom,
explain
is
that.
there a way, there's pins in there on the side.
yeah, there's just, you pull out the pin and then it just lifts up.
Alright, so
I'll go
The
help.
pin
have
on
to
the side,
FG.
so you, because it doesn't look
So
like
when you crank it all the way up, it should come off of that red piece of metal that's underneath.
okay.
You want me to go
Didn't
help?
when we latched onto the truck.
Come
I think
on.
it sounds like they need some
Lower
help.
than-
Let's go.
Mine-
Here we go.
class trip.
Okay,
I'll demonstrate.
My dad is out there, and like he has a trailer hooked up. If you want to ask him for help.
Kendra.
No,
Mr.
it's
Cunningham.
specific, I mean, my mom hooks onto these things all the
Where'd you
time,
get
so it's
that?
just,
give me like 2 minutes and I'll
Okay.
run out there.
okay, that's not a problem.
Okay.
Finish with this crew.
Okay, all right. So, stop. Okay. Okay.
Talking about you.
What did you just?
Bye, Mr.
Don't look at me.
Love you.
Dude, you have 2 minutes.
Okay. So, okay. Then you're gonna do aluminum and wood. So you're gonna hold this down, take the block, hold it at a constant velocity, get that reading, do the same thing with the static. Same thing with the cotton,
Hold it.
give that a pull,
Oh, that's
Okay.
harder.
right? And then the last thing is going to be with the sandpaper.
That's the hardest.
Don't have any other thoughts
Okay.
about sandpaper, folks.
Okay. There's that part. Now. The next part. You got this block of wood. You're going to take a 200 gram mass and set that on there. And then the only thing I want in this section is the static friction. Okay, that's it. Only the static friction. So, now, your force normal is going to be the block plus this. 200 grams is how many kilograms? 0.2. 0.2 kilograms times 9.8 is 1.96. So the total weight that you're pulling is going to be the block of the wood plus the 0.2, okay, plus the 1.96. You're going to hook that up, give that a pull,
what?
just do the static. The total weight that you're pulling is 1.96 newtons plus the weight
Oh, all
of
right,
the
got
block.
it. Yep.
Okay, then you're going to move up to a 500 gram mass, put that on there. 0.5 times 9.8 is 4.9.
4.8.
9. Okay, so then I'm going to take 4.9, add it to the weight of the block, give that a pull. Now at that point it might exceed the 2.5 Newton scale, and then you're going to have to move up to the 5 Newton scale. So get started on this.
No.
We're good?
About to leave.
Okay. All right. Okay. That's the drill. Now, we are not in any way, shape, or form going to get done with this. Just start working on this friction part today.
You got it.